Testing, can you hear me? Testing again, can you hear me? Hello, hello. Yeah, I am testing one last time, and then I will make this video public. Okay, so I am live now. So I'm going to be learning about computer architecture. Last stream, I learned about simple risk. I was reading this book. Hold on, let me just shorten the browser. And the last thing I learned was about simple risk, the assembly language. It's not implemented, but it's like an easier version of the assembly language to teach us more complex assembly languages. So this is the book, and this is the things I studied. I don't know if you guys can see. I learned about the simple risk architecture. Actually, I should go to the summary. Does the summary say it? They told us about how the machine code is actually laid out in memory. 5 bytes for the actual opcode, one for the immediate mode, whether this is supposed to be interpreted as an immediate or a register. One for the 4 bits for the destination register, 4 bits for the first source register. Actually, where is it? Where's the overall? Yeah, I mean that's the entire point. So immediate destination register, source register, modify bit, and that's the last thing I learned about the simple disk instruction set. So this this time I will be learning about the ARM assembly language, which is a real assembly language. And I also have this. I found this simulator online. I don't know how well it works, but I hope it does work. Anyways, in this chapter, we will study the ARM instruction set. As of 2010, this instruction set is the most widely used instruction set in smartphones and tablets. There's more than 90% of market share in this space. ARM processors are also one of the most popular processors in hard disk drive and set top boxes for television. What is set top boxes? Hence, for any student of computer architecture, it is very important to learn about the ARM instruction set because it will prove to be useful in the programming the mobile and handheld devices of the future. The ARM instruction set is a 32-bit instruction set. This means that the sizes of all registers are 32 bits, and the size of the memory address is equal to 32 bits. It is a RISC instruction set. Maybe I should zoom in a little bit more. With a very regular structure. Each instruction is encoded into a string of exactly 32 bits like simple RISC. All arithmetic and logical operations use only register operands. And lastly, all the communication between registers and memory happens through two data transfer instructions, load and store. The ARM machine model. ARM assembly language assumes a machine model similar to that explained in section 3.2.1 for simple RISC. Wait, I should go back to simple RISC actually. For the register file, it assumes that there are 16 registers that are visible to the programmer at any point of time. Section 3.2.1. Also, this was my drawing. I'll also make one for ARM and make this Excel. So ARM also has a 32-bit register. I don't know if it's exactly like this. 32-bit register. R0. Okay, I don't know if all of them the setup is the same as simple RISC. So 3.2 point. Okay, it assumes what again? Machine model similar to that explained over here. CPU control ALU registers. The registers are numbered from R0 to R15. Registers 11 to 15 are known by a certain mnemonic, also as shown in table 4.1. R11 is the frame pointer. It points to the top of the activation block. Hold on, hold on. So we have we put this text 15, 14, 13, 12, 11. Frame pointer points to top of activation block. 15, 14, 13, 12, 11. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is R10. R12 is a scratch register that is not meant to be saved by the caller or callee. So R12 is the scratch register. This is scratch register. What does it do? Scratch register. R13 is the stack pointer. R13 is the stack pointer. What about R14? It is important to understand that R11 and R12 are assigned a special connotation by the GNU compiler collection. They are not assigned special rows by the ARM ISA. Frame pointer at the intra procedure called scratch register, SP is stack pointer, link register, and program counter. Shouldn't the program counter be separate? Program counter and link register. Let us differentiate between generic registers and registers with special role. Registers R0 to R12 are generic. They said R0 to R12. Um, 10, 11, 12. Generic. Ten, 11, 12. The programmer and the compiler can use them in any way they like. However, registers R13, R14, R15 have special roles. SP is the stack pointer, LR is the return address register, and PC is the program counter. In this chapter, we shall use the Little Alien version of the ARM ISA and we shall describe the syntax of the assembly language used by the GNU ARM assembler. So, basic assembly instructions. Simple data processing instruction. The simplest type of assembly instructions transfer the value of one register into another or store a constant. There are two instructions in this class, move and move in. The semantics are shown below. Move register, register immediate. So destination register and source. Then move in, Oh, so it's like move, but it does the not operation first. The move in instruction flips every bit in the 32-bit register R2 and then transfers the content of the result to R1. The what do you call this? The wave symbol represents logical complement. For example, the complement of a four binary 0110 is 1001. Okay. Arithmetic instructions. Also, before go there, let's say move R05. How do I run this now? Compile failed. Bad arguments to instruction. How do I? Can I see an example? ARM version 7. Um, move R05. Wait, let me see how they did it again. Should it be star 5? Comma maybe? Total size is 8 byte. Compiled successful. How do I run the thing? What if I delete this? Yeah, I need the hash. Compile, load. No clue how to cancel. Stop, restart, step out, help. Compile and load and is clicked. The contents of the editor is uploaded to the server and saved as a single file, and run through the GNU assembler. Server then sends back the ELF executable and is any assembler output messages, and the executable is loaded into the simulator. Because the ELF file is generated on the server, there are limits on the size. Okay, but I want to see changes in the thing. Yeah, there are changes here. So it does continue, continue, restart, compile and load. How do I do the thing? Go to address register. How do I set everything to 0? 0. And now continue and load. Continue. And then this becomes 5. Okay, okay. I think I understand. If I do move not R1, R0, what happens then? Compile load 5, then FFFFFA. Okay. Yeah, I think I get it now. Assembly's instruction in this class are add, sub, RSP, reverse subtract. The semantics are given below. Add, so destination, source, source. So R2 plus R3 goes to R1. R1 stores R2 minus R3. R1 stores R3 minus R2. And an ARM assembly program to compute 4 plus 5 minus 19. Save the result in R1. So 4 plus 5 minus 19. How do you add a comment? Is it like this? 4 plus 9 minus 15. Okay. So I'm going to load R0 with 0. And then to add to R0. So actually I'm going to load in 4. And then add to it 9. Then subtract. Now add R0 plus 9. Store it in R0. Subtract what? Subtract the result of what is stored in R. So R0 minus 19. 19. And yeah, file successful. Continue. Continue. What's the issue here? 4 moving 4. 9. 13. 4. 9. What? Hold on. So 4. 4 plus 9. 4 plus 9. Or 9 plus 4. So 12 should be stored here, right? No, 13, I mean. 13. And then step over. 13 minus 19. Wait, hold on. It's 13 minus 19, right? R0 minus 4. Okay, let me see this. R to R1 minus, actually to, yeah, to R1 minus 4, 0. Then load and compile. Step over 4, 12. This, and then wait. I think I got it wrong. Minus 6, 4, 9. But how can I display this in a integer? Settings, memory access, decimal sign, minus 6. Yeah. Think this makes it much better. So, okay, I'm getting it. Logic and instruction and XOR or what is this? So bit clear, exclusive or regular or regular, bit clear. Why do we call it bit clear? So we do not of 3 and then we add it. Bit The bit clear instruction clears all the bits in R2 that are specified in R3. Okay, wait, let me think about this. So R3, R3, we do not. Okay, so the and logical operator, and 0, let's do white. If I do and this, let's say this is R2, or forget this. If I do and, the only bits that will pass down are the ones specified with this bit value, so R2, R3. So R3 has some values as 1, some values as 0. The ones that are 1 are going to get passed down. Otherwise, they will remain 0. So 0, this will pass down, this will pass down, this will pass down. I think that's a better way to imagine it. This will pass down, this will pass down, this will remain 0. Then this will pass down, this will pass down. Right? And then if I do bit clear, it is the opposite. So R2, all the bits remain as is, but the ones specified by R3 will become 0. So this will, so for example, if I copy this, the ones specified by R3 will turn into 0. 0, yeah. 0. That's the bit clear. So bit clear tells us what bits to, it uses this as a mask, and it tells us what bits to turn into 0. Yeah, then the bit clear makes sense. We shall introduce four multiply instructions with varying degrees of complexity. The fundamental issue with multiplication is that we are multiplying two 32-bit numbers, and the result will require 64 bits. Okay, my internet just lagged. Uh, the reason is that the largest unsigned 32-bit number is 2 to the power of 32 minus 1. Consequently, when we are trying to square this number, our result is approximately 2 to the power of 64. We would thus need a maximum of 64 bits. ARM has two 32 multiplication instruction that truncates the result up to 32 bits. Mul and MLA. They ignore the rest of the bits. Mul multiplies the values in two registers and stores the result in the third register. MLA is in the 4 address format, multiplies the values of two registers and adds the result to the value stored in the third register. The advantage of M&A instruction is that it is possible to represent the code sequence in the form of t is equal to plus b times c with one instruction. Such instructions are extremely useful when it comes to implementing linear algebra kernels such as matrix multiplication. So mul R2 times R3 stored in R1. And then mul with arithmetic R2 times R3 plus R4. SMUL. The SMUL and human instructions perform signed and unsigned multiplication. So the upper bits are removed, right? Is it the upper bit or lower bit that are removed? If I do uh mul R0 100 100, can I have two immediate values? 100 and 100. Register. Do they have to be register? Can they be immediate values? Move R0 100 R1 R0 100 100,000. What is 2 to the power of 60? Wait, I have a calculator. I want to know how many digits are we going across. It's to the power of 19. 32 bits. Okay, let's see. Now let's try. Let's do 9. Why 81? Look at my number here. Why is it 81 over there? Let's see. 9. What is happening? 9. Compile and load. Step over. Why is it 100? It doesn't allow it. I want to see what happens when I go over. Does it like loop around? Compile failed. I don't think it allows. The small and umal instructions perform signed and unsigned multiplication. Respectively, and two 32-bit values are to produce a 64-bit value. The semantics is shown in 4.5. R0 contains the lower 32-bit and R1 contains the upper 32-bit. Uh, R1 contains the upper 32-bit. Why did they have to reverse it? Little Adian, hold on. What is Little Adian? I need to remember. Little Adian. Little Adian is from left to right. Big Adian is from right to left. So if we are using Little Adian, control little. What I was saying is that it makes sense to store the numbers like this, where the lower bits are over here and the upper bits are over here. And my internet is fluctuating. My internet is fluctuating. I just got a lag. So they were talking about the division instructions, sign divide, you divide, where it stores the quotient in the destination register. I don't know what's up. Okay. I restarted my internet, so hopefully it works. So what I was saying is that it makes sense to put the lower upper bits here and the lower bits over here. and the upper bits over here if it's Lydian format. I was also saying that our division instructions R2 divided by R3, it stores it in the destination register. This is signed divide, and this over here is unsigned divide. R2 divided by R3 and store the quotient in the destination register. Then they were talking about that is considered the generic format of three address data processing instructions. Instruction destination operand 1, operand 2, instruction operand 1, operand 2. So operand 2 can be a register operand, an immediate or a special case of operands called shift operands. Let us describe the shifter operand in this section. So the shifter operand are these. So this is logical left, logical shift left. It shifts the ones and zeros to the left and adds a zero at the end. Logical shift right, shift the ones and zeros to the right, and then add a zero at the end. Arithmetic shift right, shift the ones and zeros to the right, and then add a 1 in the end, which is different from adding 0 in the end, and then rotate right. So this goes one step to the right, and then the last bit goes to the front. Final result, a left shift operation is present in most programming languages, including C and Java. It is denoted by the following symbol. Note that shifting a word 4-byte number by k positions to the left is equivalent to multiplying it by 2 to the power of k. This is in fact a quick way of multiplying a number by a power of 2. Let us now consider the right shift operation. Unlike the left shift operation, this operation comes in two variants. We have logical shift right, which is the same as dividing it by 2 to the power of k. Then we have the arithmetic right shift. This operation preserves the sign bit. If we shift a number right using a arithmetic shift right by one position, then we fill the most significant bit with the previous value of the most significant bit. Okay, it doesn't just add 1 on its own as the previous value. What if we shifted by 2? In a 4-bit number system, if we shift 1010 to the right by 1, then we get 1101. The original number is -6. The shifted number is -3. You'll see that arithmetic right shift divides a signed integer. Whoops. Divides a signed integer by a power of 2. Note that using the right shift operations for odd numbers is tricky. Let us consider the representation of -5 in a 4-bit number system. It is 1011. After performing an arithmetic right shift, the result is equal to 1101, which is equal to -3 in decimal. Whether we consider -2 divided by 5 minus 3 as a correct answer or not depends on the semantics of the programming language. The right rotate operation performs a right shift on the number. However, it fills the most significant bit, the number shifted out from the rightmost end. Okay, the rotate I understand. What I want to know is what if for the arithmetic shift to right, what if we are doing multiple shifts? Does it only fill the most significant bit with 1? The rest are filled with 0? I'm guessing yes, right? A shifter operand of the form R1 means that we shift the value in R1 by 2 places to the left. You know that value in R1 is not affected in this process. So we have a shifter operand. So wait, what? Um, so R2 arithmetic shift right 2. Wait, hold on. I need to go to settings and Format. Um, okay, let's just do hexadecimal. So R0 stores 1. You're going to shift it to the right. Should I shift it to the right? Or arithmetic shift? I want to see the binary though. Can I do that? Register 0. Let me see. So store 1 in this. Compile and load. Step over. So 1 is stored. And in memory, what is this E3A1? 0, 13, 5. Is this the history? What is this? I do 2, for example. And I load. It's taking its. I don't know what's happening. I may end my stream here. Okay, if it happens again, I will just end my stream. Okay, I don't know what's happening. I will end my stream here and then I will start continuing next time. I think my stream keeps disconnecting for some reason. Anyways, see you guys later then. Bye.